Hi friends, today I want to explain you about crystal field theory. So this theory was first given by the two scientists, Bethe and Walvik. What are the two scientists, ma? Bethe and Walvik are the two scientists who has given crystal field theory, and it mainly applies to the um, ionic crystals. It mainly applies to the ionic crystals. What do you mean by ionic crystals? The compounds which are composed mainly of ions are known as ionic crystals. The compounds, for example, NaCl. In NaCl is a ionic crystal because it is composed of Na plus and Cl minus. So this crystal field theory is mainly applied to ionic crystals, that is compounds which are composed of ions are known as ionic crystals, and in the ionic crystals ionic bonding will predominate. Okay, only ionic crystal is formed by the ionic bonding between the ions. Okay, and let us see some assumptions given by the CFT. What are the assumptions given by the CFT? First, it says that the interaction between the metal ion and ligand is purely electrostatic. That is, the interaction between the metal ion and ligand is purely electrostatic. Purely electrostatic. Okay, here you will see two terms, that is metal ion and ligand. Metal ion and ligand. What is metal ion? Here, according to CFT, the electron accepting group is known as metal ion. Electron accepting. Okay, and electron donating group or electron donor group is known as ligand. Electron donor group is known as ligand, and it says that the interaction between the metal ion and ligand is purely electrostatic. That is, the interaction between the metal ion and ligand is 100% ionic. And next point is it like here, according to the Christopher theory, ligands are treated as point charges. Ligands are treated as point charges. That is, here, according to the Christopher theory, the ligand, what are ligands? The species which have electron excess nature. The species which is composed of electron excess nature is known as ligands. Here, so here ligands is treated as charged particles. That is, negative charged particles. Okay, here according to Christopher theory, ligands is treated as the point charges or charged species. Okay, and according to the Christopher theory, it says that the d orbitals in metal ions all have same energy. Okay, d orbitals in metal ion is degenerative. What is degenerative? What is degenerative? Here, the metal ions are composed of 5 d orbitals. 5 d orbitals. What are those 5 d orbitals? dxy, dyz, dzx, and dx x square, y square, dz square. Okay, 1 2 3 4 5. So every metal ion is composed of 5 d orbitals. What are those 5 d orbitals? dxy, dyz, dxz, and dy square, dy square, x square, y square, dz square. And these three orbitals are considered as axial orbitals. These three orbitals are considered as axial orbitals. Sorry, not axial orbitals. And these two orbitals are considered as axial orbitals. Okay. So, uh, what are non-axial orbitals and what are non-axial orbitals? See, if you see the structure of these orbitals, first we will take axial orbitals, dx square and y square. This is x-axis and this is y-axis. So here, if you see the d x square, y square orbital, the lobes of these orbitals are present along the axis. Okay, the lobes of this is one orbital, and lobes of these orbitals are present along the axis. This is x-axis and this is y-axis. In this case, the lobes here one lobe and here lobe. So the lobes of these orbitals are present on the axis. This is, and if you see there, dz square, this is z square. Okay, the z axis dz square. Here also the lobes of these orbitals are present only on the x orbital. Z axis, the lobes of these orbitals are present only on the z axis. So this is called as dz square orbital. So here in this case, that is dx square y square dz square, all the lobes are present along the axis. If you see the non-axial orbital, see here, first what is the first non-axial orbital? D, this is y-axis, this is x-axis, this is y-axis. The orbitals d, what is the orbital? dxy. The orbitals of this, the lobes of these orbitals are present in between the axis. See, in between x and y axis, and in between this is y and this is x and y axis. Here also the lobes of these orbitals are present along in between the axis. Here also similar. D, if you see the dyz orbital, this is, let us consider y axis, and this is, let us consider z axis. The lobes of these orbitals are present in between the axis. Here also see the lobes, that is z, y. These are lobes now. The lobes of these orbitals, these are the lobes. Okay, the lobes of these orbitals are present in between the axis. Therefore, those are called as non-axial orbitals, because these are the lobes of these orbitals are present in between the axis. No? That's why these are called non-axial orbitals. What are the three non-axial orbitals? dxy, dxy, dyz, dz square. These are all non-axial orbitals. See, so here, and next one is, it says that when a complex is formed, the ligand destroys the degeneracies of this orbital. That is, how the complex is formed. How the complex is formed? When the ligand approaches the metal ion, then the interaction between the metal ion and ligand will lead to the formation of complex. Okay, so what happens during this process? What happens when the ligand approaches the metal ion also composed of electrons. Okay, and this ligand is also composed of excess of electrons. So there occurs a repulsion between the metal ion and ligand, that is d orbitals present in the metal ion and ligand. Okay, so this repulsion causes there occurs a repulsion. Why repulsion? Because the electrons in metal ions and also the electrons in the ligand leads to the repulsion between the d orbitals of the metal ion and ligand. So when the ligand approaches the metal ion, the ligand can approaches the metal ion in two ways. Okay, what are those ways? First one is when it can approach along the axis, and it can also approach us in between the axis. What is the criteria for deciding the path of the ligand? It depends upon the geometry. When the geometry of the complex is octahedral, the ligand will approach the metal ion along the axis. Geometry of the complex is in between tetrahedral. The ligand can approach the complexes in between the axis. Okay, so depending upon the geometry of the complexes, the ligand can approach along the axis, in between the axis. So let us take octahedral. Okay, first this is the 5d orbitals. Now what are the 5d orbitals? dxy, dyz, dZx d x square y square d z square. Okay, this is 5d orbital. During free, when it is free atom, the degeneracy, the energy of all the d orbitals will be same. Okay, so all the d orbitals will have same energy. That is degenerate orbitals. Those are all degenerate orbitals. As of the ligand approaches the metal ion, there occurs a repulsion between the d orbitals of metal ions and ligand. Due to this repulsion, the energy of the d orbitals will increase to some extent. What happens when there is repulsion? The energy of the orbitals will increase. The energy of the orbitals will increase to some extent. So when the ligand approaches too close to the metal ion, that is, if the ligand approaches along the axis, only the axial orbitals. What are the axial orbitals? D x square y square d z square. So the energy of the axial orbitals will increase in case of octahedral. In case of octahedral, because of the ligands approaches the metal ion along the axis, only the axial orbitals energy will increases and non-axial orbitals energy will decrease. Non-axial orbitals energy will decrease. Okay, so in this way, there causes the splitting of degeneracy. That is, the degeneracy of the metal ion will disturb, and the d orbitals will be segregated into two categories, that is higher energy orbitals and lower energy orbitals. If in case of octahedral complexes, the only the axial orbitals energy will increases, so the axial orbitals energy will increases and non-axial orbitals energy will decreases. But in cases of tetrahedral, non-axial orbitals energy will increases and axial orbitals energy will decreases. So this causes the removal of degeneracy of d orbitals. This causes the removal of degeneracy of d orbitals. Uh, d orbitals. This uh, this this splitting of this splitting of d orbitals into two categories is known as Christoffel splitting. Okay, what are the two categories? Higher energy orbitals and lower energy orbitals. The splitting of d orbitals into two categories is known as Christoffel splitting, and the energy between the higher energy orbitals and lower energy orbitals is known as crystal field stabilization energy. Crystal field stabilization energy. Okay, so what here? The crystal field stabilization energy is directly proportional to the stability of complexes. Stability of complexes. So, if the crystal field energy of the metal ion is higher, the complexes will be stable. If the crystal field energy is lower, the stability of the complexes is lower. So, this is about crystal field theory, friends. If you have any doubts, uh, comment in the comment box. Thank you for watching my video. Bye.